Good evening, everyone. Welcome tonight to this wonderful lecture about fishing for neutrinos. My name is Kara. I am the treasurer of the Stichting Professor Hendrik de Waard, together with Andra and Alexandra. We are a stichting which, together with Studium Generale, hosts a lecture also once a year about science and the impact on what it has on the planet and how to share that with everyone. But that's for later this year. Today, we want to welcome you by Studium Generale. Studium Generale is a collaboration in between Hanze Applied Sciences University and De Rug. And they host a lot of events like lectures, debates about a lot of topics, actually. If you are interested in more talks, debates, films about any topic whatsoever, a lot of culture, science, then you can go to the website. You can subscribe to the newsletter if you want to stay updated. And so thank you, Studium Generale, for having us as your host. So today, this lecture is part of a series called Let's Ask, which basically talks about the context behind very current affairs in the world. I think recently neutrinos were a lot in the news, and here Daan van Eijk is here to give us the context behind what it is, what are they, what do they do. Daan van Eijk, he studied theoretical physics in Utrecht, both his bachelor's and master's. Afterwards, he did his PhD at CERN in Geneva at the Large Hadron Collider. Afterwards, he did a postdoc for 2 years at KM3Net in Amsterdam. Afterwards, going to the USA for another postdoc for another 2 years, working at IceCube. And now, at the moment, he has a staff position at KM3Net for the last 5 years and is a guest lecturer at De Rug, which is why he's here. Tonight, the lecture will be very simple. We'll first have an hour talk of lectures. Afterwards, we have a little talk for questions. And then Daan has brought some very curious artifacts and I think VR glasses to get more acquainted with neutrinos. I hope you have a nice lecture, and a round of applause for Daan van Eijk.
Thank you. Thanks for the introduction, and thanks for having me tonight. Welcome, everyone. We switch slides. So this is what I will be talking about tonight, fishing for neutrinos in the deep sea. And I will start with a movie that I will talk you through. That's how we get this night started. So what you see here is a neutrino traveling towards Earth from the far reaches of our universe. Neutrinos are elementary particles without electric charge, and as they are very, very light, they travel at almost the speed of light. Neutrinos are highly elusive particles, so they interact with other matter only extremely rarely. High-energy neutrinos are believed to be created in extreme astrophysical environments, such as giant black holes at the center of other galaxies. And on February 13, 2023, a very, very high-energy neutrino from the distant universe crossed the Earth's atmosphere, as you can see here, and plunged into the Mediterranean Sea. And there, at a depth of 3.5 kilometers off the Sicilian coast, is the KM3Net detector, a gigantic network of high-tech light sensors. And in the darkness of the deep sea, it searches for faint bluish light emitted by secondary particles that are produced by neutrino interactions. And we were extremely lucky. With only a partially finished detector of only 21 detection lines, this particular neutrino that you see here happened to interact with matter close to our detector, creating a very strong signal indeed. This is the most energetic elementary particle ever observed by humankind. And what I hope is that you did not understand what I was just saying. If you did, you can kind of go home, because I will spend the next hour trying to explain all the little details and the bits and pieces that go into such a detection that we did. By the end of this talk, I'm going to show the movie again, and then I hope I'm going to say the same thing, and then I hope you have a feeling of, okay, now I understand what they did. Okay, cool, let's go. So why is this in a current affairs talk of Studium Generale? Because only 2 weeks ago, on February the 12th, a paper appeared in Nature that was called The Observation of an Ultra-High Energy Cosmic Neutrino with KM3 net. And that was picked up by the media a lot, both nationally and internationally. So here you see some headlines that were created in the wake of that discovery that we made. So that was really great. A little bit about myself. So I work at NICHEF. NICHEF is the National Institute, the Dutch National Institute for Subatomic Physics. And it's headquartered in Amsterdam. So on that picture on the lower left, you see me and my colleagues in Amsterdam building this detector, building part of this detector. And as was already said, I'm also a guest lecturer here at the RUG. So on the lower right there, you see me teaching a wonderful course here at the RUG to students. That's also a lot of fun. And so I wanted to point out to you, first of all, that NICHEF is a really wonderful institute, but it's also a collaboration between various universities in the Netherlands. So there you can see the logos of some Dutch universities. And of course, most notably, is the logo of the RUG, right? So that's why I'm here, and that's why we have a lot of NICHEF colleagues also here in the room. Actually, hi guys, thanks for joining. So subatomic physics. We need to talk about what subatomic physics is and how neutrinos come into that picture. So, if you ask a mathematician or a theoretician, a physicist, what do you think subatomic physics is? What does it mean? They will tell you something about the Standard Model. The Standard Model of subatomic physics, we call it. It's come to know. And they will probably say something about Lagrangians, and they will scribble things like this on a piece of paper. A mathematical equation. So they think of the Standard Model, and also I think of the Standard Model as a mathematical equation that describes exactly and with which you can calculate the chance that you see certain processes at the most fundamental level in nature. At the same time, you could also hear an answer like this. Yeah, it consists of quarks and leptons and forces, and in a sense, both are equivalent. So you could also think of the Standard Model, and this is maybe an easier picture, of the nature's building blocks. Really, what are the building blocks of nature, of everything you see around us, of matter, of all the matter you see around you. And then these are the fundamental building blocks of nature that we currently know of. So this is what we call the Standard Model. And there's a one-to-one correspondence between this mathematical equation and these building blocks. And then I was thinking of building blocks, and I have my wonderful son, Olle, who is almost 3 years old. So I'm in my Lego phase again. So I'm playing with Lego with him. And then I thought, yeah, it's a bit like this. It's a bit like Lego building blocks, right? And so I started looking around, and of course, other people had this idea as well. So really, yeah, what it consists of is these little Lego blocks. I brought a few here. And you see here in this list, again, a one-to-one correspondence between these building blocks here on the left, the quarks and the leptons, and these Lego building blocks, the quarks here and the leptons over there. Now, I will not go into detail explaining you all the different particles. What you should notice, though, is that here at the bottom, you see things like an electron neutrino, a muon neutrino, and a tau neutrino. There they are. So neutrinos, that's something important to realize, are fundamental particles, elementary building blocks of nature. And I'm going to tell you more about why they are in the Standard Model and how that works. There's some other things that you might recognize. You might recognize this one, an electron. That makes sense, right? That's something that creates electricity, all these kind of things. So there's a couple of things in here that you might recognize and other stuff that you might have never heard of. Let's take a step back to high school. Probably in high school, we all were taught the first steps of what subatomic physics is. Matter, everything that you see around you, is made up of atoms. So that's something that you probably remember, right? And then if you start to zoom in, you will see that these atoms are made of a nucleus. So there's a nucleus inside the atom, and there's electrons, circling around them, right? And then if you zoom in even more into this nucleus, you'll find that the nucleus consists of protons and neutrons. And this is probably where high school knowledge ends. But actually, if you dive even deeper, you will find that inside a proton, you will find so-called quarks. And these we saw, right? And these we currently believe are fundamental. These are the quarks, up and down in the first generation, okay? And actually, a proton consists of 2 up quarks and a down quark. In Lego language, here it is. This is a proton, right? Because this is 1 up quark, little one. This is a down quark, and then it's 2 up quarks and a down quark. This is a proton. So you see there, this is the classical picture that we were taught at high school. An atom consists of a nucleus with neutrons and protons and an electron circling around it. So here we have it. Here's your electron, right? It's over here. And then you have your proton. And now the only thing I still have to explain of what is in the atom is a neutron. And a neutron, as it turns out, consists not of 2 up quarks and 1 down quark, but of 1 up quark and 2 down quarks. So it looks a little different, right? Proton, neutron, and an electron. And this explains everything that you see around you, that you're used to. The floor, the earth, the air around you, that you breathe, your loved ones. Everything consists only of these particles, protons, neutrons, and electrons. That's kind of amazing. Everything you see, everything you know of, only consists of these little tiny pieces. So you might wonder, okay, nice that you told me this. What does this one have to do with it? Why do you need an electron? Why do you need a neutrino then? Because I just said we don't really need it. We just need these 2 up and down quarks and the electron, just 3 particles. Here's the reason why. So now we go back to history again to explain you how this neutrino made its appearance in the Standard Model. So we're here in the early 20th century, and there's a problem. So particle physicists have a problem with energy conservation. This is the era in which people discover radioactivity. So people are doing tests in the lab, and they find that that the nuclei of atoms some of them are unstable. And they are unstable, and when they do, they sometimes decay an electron, this one. So sometimes it just happens that you have the core of an atom, and somehow a proton suddenly, the nucleus suddenly emits an electron out of nothing. Radioactivity, out of nothing, it just creates radiation. And here's the weird thing. So what they knew was happening was that this proton was somehow converted into something else, and this electron came out. So if you do such an experiment and you start measuring the energy of this electron that comes out, you would expect that you would always measure the exact same energy, right? It's 1 particle that falls apart into other particles, and then you can, by the conservation of energy and momentum, you can tell this should always have the same energy. So if you would plot that, maybe on this plot where here is the electron energy, you would expect a spike here. So if you measure this thing 10 times, you would find 10 times this energy. That's what they expected to see. That's not what they found. They found this. A continuous spectrum of energies. Sometimes they found a very low energy of the electron, and sometimes it was extremely high. They had no clue. It was impossible. If it really was true that this is 1 particle falling apart in these 2, then this electron should really always... So people were really puzzled, and they thought, okay, then maybe conservation of energy is not true anymore, and that would really shake the foundation of physics. So that was not the way to go. But then some clever people thought, we recognize this, and we have one idea that could save us. And this was the idea. They introduced, they postulated, they came up, they dreamed up another particle. They dreamed up the neutrino. Because if there's another particle in this decay, then the energy is shared between these 2 particles. And sometimes this carries a lot of energy and this very little, and sometimes this one carries little energy and this a lot, creating a continuous spectrum. Right? Now this idea was introduced in a very funny way. It was introduced by Wolfgang Pauli, an Italian physicist. And this is in the 1930s. So on the left, very cool, typewritten letter sent to his colleagues. On the right, you see the English translation to make it easier. And there's just a couple of things that I want to take out of this nice letter. So first of all, it's 1930. So it's 1930. And Pauli says, "Dear radioactive ladies and gentlemen," that already sets the stage, right? He knows radioactivity is the thing of the day. And he writes this letter because he needs to attend a conference, but I'm now going to skip to the last line, but he says, "Sorry, I cannot personally appear in Thuringen since I'm indispensable here in Zurich because of a ball on the night from December 6 to 7. He's just going to party. You're going to say, sorry, I'm not going to come. I have a party." But he did have a brilliant idea. I always think that the idea that he wanted to put forward was so revolutionary that he didn't dare to go. But I don't know if this is true. But anyway, what he says is, "I have a desperate remedy to solve this problem that we find." And he says there could exist electrically neutral particles, which I will call neutrons. This is a historical fun fact. Later, the actual neutron was discovered. And so they had to find another name for this particle that he introduced, and they called it the little neutron, the neutrino. That's why it's called ino, which is small in Italian, right? The mass of this neutron should be very small, not larger than 0.01 of the proton mass. And he says, "I admit that my remedy may seem almost improbable, but nothing ventured, nothing gained," which sets the stage for neutrino research in the next decades. So he has this brilliant idea, and it's a nice way to postulate this idea. And later he will remark, so this is him, and he will say, "I have done a terrible thing. I have postulated a particle that can never be detected." Because here's the thing, if it was able to detect neutrinos, they would have seen it, right? So the fact that he really had to come up with this particle means that it cannot be detected, right? That's why he said it. Now, this is a thing that you should never tell an experimental physicist. Never tell an experimental physicist this cannot be done, because they will try. And so we tried. And here we go. But it takes a while. It's now 1956. There's a war in between, the Second World War. And after the discovery of radioactivity, there was a lot of research on radioactivity, which then naturally flowed into the study of nuclear fission. And then, of course, you can do terrible things with that, making an atomic bomb. But you can also do wonderful things with it, and that is to harvest energy in a nuclear fission reactor. So this is a picture of a nuclear reactor. And after the war, so in 1956, it was kind of like experimental physicists were looking for a job. The Manhattan Project, the making of the atomic bomb, was ready. That was done. And so they were looking for a challenge. Well, finding neutrinos was a very big challenge. And then people were thinking, maybe here in these nuclear reactors are exactly the right circumstances to make neutrinos. So what happens, the products of nuclear fission sometimes undergo a certain decay where a neutron decays into a proton, an electron, and a neutrino. And so people were thinking, maybe we can detect these neutrinos. Okay, first of all, I want to show you something here, this little electron that you see here. This is the thing that causes this weird bluish light in a nuclear reactor. And I want to draw your attention to it because it's going to take center stage in the story later, this bluish light. So remember this bluish light that is caused by an electron, okay? But that's not what I wanted to say. I wanted to say, how can we detect this little neutrino over here? How can we do that? So the good thing that people realized in the 50s was the flux that is coming out. So the number of neutrinos per square centimeter per second that is coming out from a nuclear reactor is enormous. Billions and billions of neutrinos every second. So people thought, we might be able to do something with it. And then there were two US particle physicists, Raines and Cohen, and they actually did the job. So they were relying on kind of the inverse of this process, where a neutrino interacts with a proton, and out comes an electron and a neutron. And they somehow, I'm not going to explain you how they were able to measure this thing. And again, they also announced this in a very nice way. This was the time of telegrams. So this is the original letter by Pauli, right, on the left. And then here on the right, you see the telegram on the lower left. And it's very hard to read, so I'll read it for you. It says, we are happy to inform you that we have definitely detected neutrinos from fission fragments, blah, blah, blah. And they sign it. And they send this telegram to Pauli. 26 years after he dreamed up this particle, he gets a telegram out of nothing saying, we did it, it's true, this is real, it happened. And then he writes back, he writes a little note and he says, thanks for message, everything comes to him who knows how to wait. Pauli. 26 years. Okay, so now that you know that the neutrino is real and why we need it and that it really exists, I'm going to tell you something about neutrino sources. Well, we found one already, right? A nuclear reactor is a source of neutrinos. In the same energy range, roughly in the same energy range, we have the sun. The sun is also emitting billions and billions of neutrinos every second with roughly the same energy as in nuclear reactors. Also supernovae, so these are exploding stars at the end of their lives. They implode and then blow out all the mass that is surrounding the star. And in that explosion, so to say, also a lot of neutrinos are emitted, also in that same energy range. Then, at even lower neutrino energy, so here if you go to the right in this picture that is increasing neutrino energy, so at very, very low neutrino energies, we see neutrinos, or we think there are neutrinos, because we have never seen those, from the Big Bang. So the start of our universe, at the start of our universe, that is such a high energy event that we also expect a lot of neutrinos from there. But that was 13 billion years ago. So these neutrinos have been traveling for so long that the energy is very low by now. So they were very highly energetic, but now they're not so much anymore. And then we have two other sources. One is accelerators, the LHC. So the LHC is the Large Hadron Collider at CERN in Geneva. This machine is smashing protons together, so two of these guys, right? So you have another one coming in and then they smash them together. Also in that process, a lot of neutrinos are created. And then we have something that I will also come to talk about a little bit more later, is cosmic rays. Now, cosmic rays are also known to exist already for 100 years, and these are charged or even uncharged high-energy particles coming from the far universe. But when they impinge on our Earth's atmosphere, they create what we call showers of secondary particles. And in these particle showers, there are also neutrinos. So in a sense, the atmosphere is also a source of neutrinos, but it's secondary, right? So there's an original particle coming into the atmosphere, and that creates a lot of neutrinos. So our atmosphere is constantly bombarding us with neutrinos. And then finally, these are the highest energy neutrinos that we know exist. And these are emitted in what we call, we call these active galactic nuclei. So we know that at the center of galaxies, there's massive black holes, and they're kind of swallowing in matter and radiating that out again. And in that process, very, very high energetic, actually the highest energy neutrinos that we know are created in such cataclysmic events in the far universe. Okay, so that's about neutrino sources. What are these neutrinos? They're super weird particles. I want to explain you a little bit why they behave as they behave. I'm just looking, Annelies, is there a clock somewhere where I can see how long I can see? Otherwise, I just keep talking. Thanks. Okay, neutrinos are very abundant. There are 65 billion solar neutrinos each second passing through only the area of your finger, of your thumbnail. 65 billion solar neutrinos each second. So now 65 billion, 65 billion, 65 billion neutrinos from the sun. And it doesn't matter, the sun has gone down now, but actually they are coming right through the Earth. I'm going to explain you why. Dankjewel, Lieke. Super. So 65 billion solar neutrinos each second. Yeah, I'll put it here. Yeah, dankjewel. And still, they almost never interact. That's so weird about neutrinos. They almost never interact with any matter. So if you keep looking at your thumbnail for 300 years, and each second 65 billions are coming through, it will take this 300 years before you expect one to have an interaction with your thumbnail. The other ones are just whizzing through. That's why we sometimes call these neutrinos ghost particles. They're extremely elusive. They pass through everything. They don't see the Earth. They go right through the Earth. It's crazy. They're crazy particles. So if you do want to detect them, since the chance that they actually undergo an interaction, which gives you a chance to observe them, you'd better build very big detectors, right? So the business of doing neutrino physics, of studying, of detecting neutrinos, you need two things. You need to build very big detectors, and you need to be patient. Pauli already said it. You need to be patient in this business. Here we go. Here's one of the first large-scale neutrino experiments. It's the Homestake experiment. Here you see for scale a person standing on top of a large vessel in which there's a special material that can detect neutrinos. And this Homestake experiment has been running from the 1970s to 1994. And it actually ended with a big question mark. So they did observe solar neutrinos, but I'm going to explain you what they did not see. So here's the reaction. Again, the same thing. So you have an incoming neutrino, and it undergoes an interaction with chlorine. So this vessel is filled with chlorine. And then you expect that an argon atom is being made. That's the secondary particle, and also an electron. And this is a wonderful experiment. It was undertaken actually not by a particle physicist, but by a chemist. And the chemist, this person, he said, yeah, I know how to do this. I'm just going to purge this vessel every week, and I'm literally going to count the argon atoms. So he knew a way of counting, literally counting the argon atoms. And the number of argon atoms was the number of neutrinos that he expected. And it was roughly 2 or 3 per week. He was able to count argon atoms. Unbelievable. But as I said, after doing that for 24 years, here's what he found. I'm going to show you this plot. Here in yellow, you see the theoretical prediction made by theorists who say they know how the sun works. So we know how the sun works. It's nuclear fusion, right? You have nuclear fusion fueling the sun. And we expect this many neutrinos. They gave the number here. This is what you should measure. After 24 years of measuring, this is what this experiment found. Roughly a third. Roughly a third. Okay, not cool after 24 years. So they did find neutrinos, sure, but too little. Then they built a lot of different experiments afterwards. It's called Super K, Kamioka, SAGE, GALEX, GNO, SNO. And what do they find? They all find too little neutrinos. All roughly a third. It's like 2/3 of neutrinos are missing. They're gone. What? Okay. So you build more detectors and you're more patient. But what you can also do is build smarter detectors. And that's this SNO experiment. It could not only detect this thing over here, but it could also measure all neutrinos. And now we come back to this picture over here. Remember that there were actually, I didn't point that out, but maybe you noticed. There's actually 3 types of neutrinos, right? Electron neutrinos, muon neutrinos, and tau neutrinos. And all these previous experiments could only measure electron neutrinos. And this final experiment could measure the total sum. They could measure all of it. And if you add that all up, it does match. So somehow, this is the weirdest thing I know about neutrinos. They oscillate. So in the sun, you create only electron neutrinos. If you measure them at a later point somewhere between the sun and the Earth, the mixture is different. And then if you measure them here on Earth, you measure only a third of the original. Here you have 6, here you have only 2. They change identity, literally, as they travel. This is extremely weird. It's wonderful. Anyway. It will not be so important for the rest of my talk, but I just want to point it out to you because it's so wonderful. Okay, so neutrino recap. There are extremely many neutrinos. There are multiple neutrino sources yielding different neutrino energies. Neutrinos almost never interact with any matter, and they change identity as they travel. Okay. Then the question is, are we done now? No, we're never done. Can we build even bigger neutrino detectors? Of course we can. Well, the real question is, of course, why would you build an even bigger neutrino detector? And I'm going to explain you this with a plot again. So bear with me. I'm going to explain you everything that is on this plot. So here on this axis you see the flux. So that means the number of neutrinos per square centimeters per second. Okay, so number of neutrinos is what you should remember. So this is more neutrinos and this is less neutrinos, right? And then on the other axis you have neutrino energy, where to the left is lower neutrino energy and to the right is higher neutrino energy. Oh, and I wanted to point out these units that you see here on the bottom. This EV, it's called an electron volt. I'm not going to explain you what it is. It's the favorite energy scale of particle physicists. We think in electron volts. And you can compare it with something in bytes, right? So you have 1 byte, but then you have also 1 kilobyte. And an old floppy disk could contain 1 megabyte. And then you have your USB stick that typically contains 1 gigabyte. So there's also something funny on this axis, right? It's not +1, no, it's times 10 times 10 times 10 times 10 times 10. So this is an enormous energy scale, right? So that makes this plot a little weird in that sense. And here it is. Here's the picture of all the different neutrino sources that I told you about before. So these are the cosmological neutrinos. These are the solar, supernova, power plants, atmospheric neutrinos, and these AGN neutrinos, astrophysical neutrinos. And here we are at the end of at the beginning of the 2000s, right? So early 2000s. And this is the energy range that we have covered so far in neutrino energy. Because the only neutrinos that we have seen so far are solar neutrinos, supernova neutrinos, and power plant neutrinos. That's about it. And they all live here, in this green area. There's a vast energy range where we haven't seen neutrinos yet. And that's, of course, where we want to study more neutrinos. We want to study other neutrinos. Now, to the left of this, forget about it. It's too difficult. The energy of these neutrinos is too low. So we're not going to go there. But here, on the right, at higher neutrino energies, we do expect that we can detect them. The only trick is you need to build big. Because as you see, the flux, the number of neutrinos, is going down the higher energy you get. So to the right in this plot, you'll see that the flux is dropping. So less neutrinos. The chance of detecting a neutrino kind of stays the same. So if you want to detect a neutrino anyway, you'd better build large, right? The larger you build, the bigger the chance that you actually measure something. Okay, so how big does it need to be? People do some calculations and they say, roughly a kilometer by a kilometer by a kilometer. And that's 1 cubic kilometer. And that explains the name of the experiment that I'm working for. It's called KM3net. The KM3 stands for cubic kilometers. That's what we're trying to build. We're trying to build a neutrino detector that is 1 cubic kilometer. And NET stands for neutrino telescope. And that also becomes clear now why it's... So we want to study neutrinos, that's clear. And we call it a telescope because we want to measure these neutrinos that are coming from the far reaches of our universe. And that's why we call it a telescope, because people historically have always looked at the night sky with telescopes, right? And we're basically looking at the sky. Final reason to build even bigger neutrino detectors is the following. Here is such a very high energetic event somewhere in the cosmos, right? An AGN or a black hole, a massive black hole. We expect that there's many particles coming from such a thing, actually. We expect, for example, a lot of photons, so light particles coming out, but they can be absorbed by molecular clouds that are somewhere in between the line of sight to the Earth. So yeah, you cannot really measure how many they're coming from because some of them are absorbed. Then you have also protons, these ones. They're also emitted by these black holes, but these are charged particles, and there's a lot of magnetic fields between such an object and the Earth, so they'll start spiraling around. They're deflected. So if you measure them coming from there, there's no way that they're actually coming from there. They're probably coming from there, but they've changed course. There's one wonderful particle that doesn't do all that stuff, the neutrino. You guessed it, right? The neutrino is coming here and is coming straight to Earth. It doesn't interact with anything. That's wonderful news. It makes it a wonderful messenger of what's happening there, but they're terribly hard to detect. That's the problem. One more thing. Where would you build such a big neutrino detector? Where can you build a kilometer that is a detector that is 1 kilometer by a kilometer by a kilometer? Not so easy. Thanks. Yes, underwater. But why? I'm going to explain you why. And it's coming all back to these cosmic rays, right? These cosmic rays are particles that are coming from the universe and are impinging on our atmosphere, and they're creating secondary particles. As I said, there's neutrinos in there, but there's more particles in there. And here you can see such a shower. So here you have what we call the primary cosmic ray. It's coming in. It undergoes an interaction with the proton, and then out come a lot of different particles. And the particles that survive longest, they're only of 2 types. One is a so-called muon. Actually, it's this one. Well, it doesn't really matter. The orange line here. And the other ones are neutrinos. The blue line here. And those are the ones we're interested in, right? Now imagine that you would build your detector roughly at this level. Yeah, then you're measuring these muons also. Their background. So you think that you're looking at a neutrino, but you're looking at a muon. Not good. The good thing is that these muons, they don't penetrate the Earth fully. Actually, they stop at a certain point. So the deeper you go, the less muons. And the neutrinos survive. They go right through everything, right? Those are the ones that we want to measure. So deep. Whatever you do, if you build neutrino detectors, you should build them deep. Okay. This is a picture taken very recently, I know, because it's one of the largest underground cavities ever excavated by human beings. So very deep in a very deep mine, I think 1.5 kilometers down or something. You want to know what they're going to build in this cavity? A neutrino detector, yes. They're building a neutrino detector right next to that homestake experiment that you saw before. So they're trying it, but the real question is this 1 kilometer by a kilometer by a kilometer? No, that's never going to work. So you might ask, why are they building a neutrino detector here? Because it's right in the way of a particle accelerator. So this is a smart way where we actually shoot neutrinos and we know exactly where they're coming from. So then we can actually very targeted look, and then it's easier. So then this is big enough. But for these very high energy neutrinos that we want to measure from the outer cosmos, this is not big enough. So the answer is not in a mine. In a mine, we cannot dig out 1 kilometer by a kilometer by a kilometer. Impossible. So here it is. Here you have your requirements for building a neutrino detector. It needs to be 1 cubic kilometer in size, and it must be as deep as possible. Well, you guessed it, underwater, or in deep ice. So this was in the 1970s. 1970s, people were drawing this up and thinking, that might be a good idea. Again, you have to be patient. They tried from the 70s onwards. They tried it for 20 years, I think, in the Indian Ocean. Didn't really work. Then they started building in Lake Baikal in Russia, and it has taken them roughly 20 years to get up to speed, and now they're actually building a large detector in Lake Baikal. It's difficult. These are terrible environments to build something in. Very deep sea, very deep ice. It's really not easy. The first one that was really successful was the ice cube detector, built between 2005 and 2010, built exactly at the geographical South Pole. So the exact South Pole, there's a large base, here it is, so here's the ice cube laboratory. Data is collected there, and what they've done is they drilled through the ice with a hot water drill. They drill kilometer-long boreholes where they lower long strings with optical modules. They look a bit like this. And they built this giant array, a three-dimensional grid of these detection elements, and they built the first neutrino detector. And they actually measured these high-energy neutrinos. I'm going to explain you how high energy they were and what they found. And then we started building KM3Net from 2015 onwards, and we're still building it at the bottom of the Mediterranean Sea. So this is kind of an artist's view of what our detector looks like at the bottom of the sea. It's really this three-dimensional grid of all these optical modules. And here you see one of these optical modules for real. This is what they look like. So we're basically building a large three-dimensional array underwater of these things on long vertical lines. Of course, you could never look at this like this. So we're building this very deep in the sea, so it's pitch dark there. But you want to show something, that's why you see light here. Okay, but how to detect such a neutrino? Why do we build a detector like this? That's not a requirement, right? Before you build a detector, you should know, what do I actually detect? Okay, here's a thing that you might already know by now. There does not exist a neutrino detector. A neutrino detector is not a thing. You cannot go to a store and say, give me a neutrino detector. There's not a single material that says, I have detected a neutrino. That doesn't exist. Well, what we can do is this indirect measurement. So here you have an incoming neutrino. Imagine that we're lucky and that one of these neutrinos undergoes an interaction with the seawater, with a molecule of water, right? With a nucleus over there. And then we have seen many times now already that it somehow transforms into this muon. And this muon will travel through the water. Bad thing. Also, a muon detector doesn't really exist. Well, there kind of is, but you're not going to build it underwater. So there is indeed a way to detect muons, but we do it again indirectly. So how do we do it? And now I have to draw an analogy. What you see here is a fighter jet, obviously. And you probably know what happens here. So when this fighter jet is passing the sound barrier, we call it, it will move faster than the speed of sound in air, right? And what do you get then? Do you know what happens? A sonic boom. Very good. Completely analogous to this. Oh, by the way, you've never seen this. What happens here is that since the sonic boom, so sound is a pressure wave, right? It's an air pressure wave. So the air is so much compressed here because of this shock wave. It's a shock wave of sound going through the air. And so the air here is so much compressed that the moisture in the air starts to condense. And so you see clouds. So clouds that exactly outline the shock, the wave of the shock front. So it's the shock front that moves through the, and it's this cool conical structure. And if you follow this conical structure, in the center is exactly the direction in which the jet is going. That's really cool. So if you were only to see this cone, I could tell you, probably this jet was going in that direction. And that's what we do. Because this is exactly analogous to what happens in our detector. Imagine that the muon, this muon that was produced because of the neutrino interaction, if that starts moving through the water, it will move through the water, and listen carefully, it moves through the water at a speed that is higher than the speed of light in water. Now, you might have learned in high school that nothing can go faster than light, and the speed of light in vacuum is fixed and constant. That is all true. But in a medium, like water or ice or even air, the speed of light is lower than the speed of light in vacuum. And this muon will travel almost at the speed of light in vacuum, which is faster than the speed of light in water. And analogous to the fighter jet was going faster than the speed of sound in air, it will create not a sonic boom, but a... Sorry? An optic boom, yes. An optic boom, because this was light, right? Air was a pressure... An optic boom. That's what it is. This is an optic boom, and the shock front is exactly here. And the real cool thing about this is that it emits this bluish light. It's the same stuff that you see in a nuclear reactor, right? And we can detect this. These are photons, light particles. So imagine that you're deep down in the dark sea and all of a sudden you see a blue light. That's what we try to detect with these things. And then based on, we know that it should be something like this. This should be the shape. So if we accurately time all these sensors, we can kind of reconstruct what the shape of this shock front is. And therefore we know exactly where the muon was coming from, which then exactly translates to where the neutrino was coming from. Okay, I've already done it, but now I really want to explain what this KM3net optical module is. So what you see here is a big glass hemisphere. And inside that hemisphere, you have 31 of these, what we call PMTs. And a PMT stands for photo multiplier tube. This is kind of an inversion of a light bulb. So if you have a light bulb, something that just powers light here, in such a thing, you put in electrical power, and out you get light. This works the other way around. In pitch darkness, if all of a sudden I have a photon, a light particle coming in, it will create an electrical signal that we can read out through this little cable over here, right? So it transforms light into electricity. And so what we do is we have this 3D printed structure and we put these PMTs in. We do that 31 times and then we put it into this glass sphere. And I will show you a fantastic movie. Later you can have a look and I can explain whatever you want. And I'm also going to show you a movie of how we build these things. Okay, so here we go. Since we detect these neutrinos by detecting light, as I explained to you, in the deep sea, we construct our detector as a three-dimensional array of optical modules, right? That detect light, arranged along very tall, flexible detector lines. So we put these optical modules on very long lines. Now, KM3net actually consists of two geographically separated neutrino detectors in the Mediterranean Sea. That's an important detail. And in this animation, you kind of see them next to each other for scale comparison. The smallest detector, which is that small little cube that you see there, next to the Eiffel Tower, is called KM3net Orca. And that will ultimately consist of 115 detection lines. Now, there are 18 optical modules on each detection line, so that leads to a total of roughly 2,000 optical modules in KM3net Orca alone. The vertical spacing between these optical modules is roughly 9 meters, and the detection lines are therefore 200 meters long. So in this movie, these things are 200 meters long. Now, you can compare that to the size of the Eiffel Tower. That kind of matches, right? The horizontal spacing between the detection line is 20 meters. That's really incredible because the detector is deployed at a depth of 2.5 kilometers deep and is situated 30 kilometers off the coast of France. So here you see the outline of France. This is the Mediterranean in white. And this is the site of our smallest orca detector, this one. That one is located there. Now the large detector that you see actually consists of 2 building blocks. So it's 2 blocks of 115 lines, right? So that will have 230 lines in the end. And that is the one that will instrument 1 cubic kilometer. So these 2 building blocks is actually 1 kilometer by a kilometer by a kilometer. And this is the one that is actually tailored to measure these very high energy neutrinos from the cosmos. The vertical spacing between these optical modules is much larger, 36 meters, and therefore these lines are much longer, 800 meters long. Imagine that you're standing at the bottom of the sea and you have an 800 meter long line above you. It's really incredible. The horizontal spacing between these detection lines is 100 meters, and this one is deployed at a depth even deeper, 3.5 kilometers deep, and is situated 100 kilometers off the coast of Sicily. You can see it right there. So that's where our second detector is. So this large detector geometry is chosen to detect and precisely pinpoint neutrinos from these astrophysical sources in outer space. And in that sense, this is the detector that is suited for this astrophysics research. Okay, currently, at this moment, as we speak, we have deployed only 24 detection lines in this small detector and 33 in the big one. So we're far from done. And still we're doing really great science. And we have... we're collecting data as we speak, so that's really great. Okay, so in this movie, I'm going to show you another movie. I will show you how you actually build such a detector. So this is the last movie that I show, and then I'll go on to explain what we actually discovered and why I'm here today. So I will show you how we build our optical modules and these detection lines. So here we go. This optical module is really the basic building block of our detector. So there are 31 PMTs, as I said, in each optical module, these photomultiplier tubes, that can register the Cherenkov light, this bluish light. And these light sensors are assembled in glass half hemispheres that are designed to withstand the extreme pressure of the deep sea. These half hemispheres are then sealed together to form one optical module. Each optical module is then tested and calibrated before moving to the next stage of production, which is to connect 18 of these optical modules to an electro-optical cable to form a detection line. This electro-optical cable is this pinkish cable over there, actually made in the Netherlands, really cool. And that is really the backbone of our detector, supplying power to the optical modules and carrying the data on optical fibers back to shore. Now, in order to deploy our detection lines, we carefully insert them into this large spherical structure that you can see in this nice time-lapse video over here. So we insert 18 modules and this electrical cable in this spherical structure. And once all these 18 optical modules are loaded, we put this structure on a yellow anchor. So these are the yellow structures there, which are really just blocks of steel that firmly ground the detection lines to the sea bottom. And then up is deployment, where each detection line stack is carefully lowered to the depths of the Mediterranean Sea. This is a process that typically lasts a few hours, so it takes a few hours for that stack to go down. As the Mediterranean, as I told you, is very deep, and this needs to happen very, very gently. Now, in parallel to this, we also deployed these small remotely operated submarines, and they can perform specific tasks at the bottom of the sea. So this is one of them, and they can perform visual inspection for us. And here's a guy that just uses a joystick and draws the things around. So we let this submarine connect the detection lines here to our junction boxes. So here you see one of our junction boxes that provide power and data connections. And now comes the very, very exciting part of unfurling the detection line. So here we let the submarine pull a mechanical trigger. Here it goes. Wait for it. Bam. And this releases the spherical structure, and given the buoyancy of that structure, it will float upward and unfurl the detection lines, pulling out the optical modules one by one. This is really astonishing that this idea was invented in the Netherlands, by the way. It's amazing. The empty sphere just comes up back to the surface, and we reuse it to build new detection lines. Yeah, it's really amazing. So here are the optical modules in their final configuration. Here it is. So this is the visual inspection of the line. And given that the detection line is influenced by the sea currents, there are sea currents, right? So the detector is moving. So we need to keep good track of the positions of the optical modules. And to that end, there's a compass inside each of these things, and it's also part of an acoustic positioning system. Now, moving back upstream from the junction box all the data and the power is routed through this main electro-optical cable that runs back to shore to our shore stations. So we have one shore station in southern France for this small detector, and another one in southern Sicily here for the large detector. And this is the place where all these optical fibers arrive on shore and where our data is carefully time-calibrated with sub-nanosecond accuracy in order to precisely reconstruct the particle tracks through the detector. The shore station also houses all the power supplies, the monitoring, the control systems of this entire infrastructure. And our data is then carefully checked, processed offline by running our reconstruction, calibration, analysis software. Well, needless to say that building and operating such a complex detector and infrastructure requires a tremendous team effort and collaborative spirit. So here you see where all these detector elements are made throughout Europe. Throughout Europe and beyond, actually. And here you see a picture of all our teams of technicians that are building our detector. Okay, that was a long story. I hope you enjoyed the movie. I can tell you later about all these wonderful things that you've seen. But now I want to come back, and then it's almost time to wrap up. I come back to this discovery that we made and that we announced 2 weeks ago. So this is the title of the Nature paper. It's called Observation of an Ultra-High Energy Cosmic Neutrino with KM3 Net. And this is a picture of it. So by now, I hope you kind of have an idea of what you're looking at. So here, anchored to the sea bottom, you see these anchors, right? And here we have our long vertical lines, and every dot here is one optical module. At the moment that we made this detection in 2023, the detector was consisting of 21 lines only. So at that time, there were only 21 lines in the water. And obviously, this is not an actual picture, right? This is a reconstruction of what we saw with our detector. So this is a result of our reconstruction software that, as I said, reconstructs this Cherenkov cone, right? And from this Cherenkov cone, we can infer that the neutrino was coming from somewhere there. And we call this event, and it's useful to give these events a name. I mean, it's not a wonderful name, but we call it KM3 230213A. That's just the date, and the A stands for the fact that later that day you could have another one that you would then call B. But okay, this is A. And I want to place this discovery in context, because here it says it's an ultra-high energy cosmic neutrino. Yeah, okay, but what does that mean? So we have already looked at this graph, right? Where here we had the flux on the vertical axis and the neutrino energy on the horizontal axis. And I told you, why do we want to build these big neutrino detectors? Because we want to explore this yellowish, orange-yellowish area, right? I also told you about the IceCube detector. That has been running quite a long time already, and they actually saw these high-energy neutrinos already. So they extended this range. Look, I'm switching between the slides. This is before IceCube, and this is after IceCube. So IceCube has detected these high-energy astrophysical neutrinos. We know they exist, and this is what IceCube did. And so we were kind of hoping that there still was something in store for us, for KM3Net, and that IceCube didn't take away all these discoveries, and we were lucky, because where's our event on this scale? It's there. It's in this yellow area. It's far beyond anything that IceCube has ever seen. In fact, this event is 30 to 40 times, and that's a conservative estimation, 30 or 40 times more energetic than anything anyone has ever seen. So this is really the highest energy elementary particle that humankind has ever observed. And it's right in this unexplored region. It's something new, something strange, something we don't know, and honestly, something we didn't expect. You can see these AGN neutrinos, these astrophysical neutrinos, here you actually see that even that flux is dropping before our event. So we expect almost nothing there. So it might be a completely new category of ultra-high energy neutrinos created very far away. That's why this is exciting. That's why this is new. So it's really a gift from the universe, you could say. So just some numbers. It's 10,000 times more energetic than LHC particles. So the LHC is the biggest machine mankind has ever built to smash protons together. And the thing that we see here is 10,000 times more energetic. It's laughing in the face of the LHC. It's nothing, peanuts. Highest energy fundamental particle ever observed, as I said. And it's 40 times more energetic compared to IceCube's highest energy neutrino. As I said, conservative estimation. But there's many open questions. Where does it come from? We don't really know. So even though we can reconstruct this Cherenkov cone and point it back, we cannot really pinpoint the source at this moment. We actually try to see if there's something there in the sky. So what we do is we just extrapolate back this point and we look in the night sky. Is there something there? Something that we already know? And we look, yeah, there's multiple things. You always find something. But we haven't been able to really say it's that source. Okay, so we don't know where it's coming from. Or, that's something that I hinted to also, is this maybe a first discovery of something completely new? And then we call that a diffuse flux of so-called cosmogenic neutrinos. For the people in the room, I'm not going to explain this, but for the people in the room who might understand this, what we are thinking of is that this could be a neutrino, or actually cosmic rays that are having interactions with the cosmic microwave background. I don't know if cosmic microwave background says you anything. That would also create extremely high energy neutrinos that we never dreamt of detecting already, but we might have detected something like that. Another very relevant question is, why didn't IceCube see such a neutrino? IceCube has been running with a very large detector, almost 100 detection lines, for almost 10 years now. They haven't seen such a thing. So are they extremely unlucky? Are we extremely lucky? We don't know. You can do a back-of-the-envelope calculation, and it turns out that if naively, if you look at this flux, you would expect that with these 21 detection lines, we would have had to wait 70 years before finding something like this. And we find it now, after a couple years. So yeah, we could be extremely lucky. What I'm going to do next is the last thing. Now that you've heard all this, it's almost been an hour, so I'm going to wrap up. I'm going to show you the same movie again, and I'm going to read the same text again, and now I hope that you can kind of take it in all again and that it makes more sense to you now. And after that, there's time for questions. So here we go. So here you can see a neutrino traveling towards Earth from the far reaches of our universe. Neutrinos are elementary particles without electrical charge, and as they are very, very light, they travel at nearly the speed of light. Neutrinos are super elusive particles interacting with other matter extremely rarely, almost never. High-energy neutrinos are believed to be created in extreme astrophysical environments such as giant black holes at the center of other galaxies. And on February 13, 2023, a very high-energy neutrino from the distant universe crossed the Earth's atmosphere and plunged into the Mediterranean Sea. And there, at a depth of 3.5 kilometers off the Sicilian coast, is the KM3 detector, a gigantic network of high-tech light sensors. And in the darkness of the deep sea, this detector searches for faint bluish light emitted by secondary particles that are produced by neutrino interactions. We were extremely lucky. So with only a partial finished detector of only 21 detection lines, this particular neutrino happened to interact with matter close to the detector, creating a very, very strong signal indeed. And this is the most energetic elementary particle ever observed by humankind. And we will continue to do so in the next years. So, thank you very much. Are there any questions? Oh, yeah. I leave it up to you.
The event was called 230213, and the New York Times article you showed was from 2025. So what took 2 years?
It's a very good question that we often get. So, first of all, to be quite honest, we kind of missed it at first. So it was really, what you should realize is when we get all the data, it really takes a while before we really process all our data, calibrate everything, do simulations to see if we understand what it is. This event was so far off from anything on our scale that we were hoping to measure that we kind of missed it at first. So I think it was about a year ago, so after a year, that people said, let's dive into it and see if it's really something there. So that was a year ago, and then we really started doing a lot of checks because this was so unexpected. So we did a lot of extra simulations, see if we could simulate this event and understand how it would show up. We also used these simulations, by the way, to estimate the energy. So we did a lot of systematical studies, recalibrations, really understanding this signal, and then we thought, yeah, it's real. We have tried everything to debug it, and it's not a fake signal or anything. It's real. And then we decide together in a collaboration that you want to publish this, and then we thought, okay, this is big, so we're going for Nature, and then the process for Nature is not so easy. That will take you at least 4, 5, 6 months before it's really there, and that easily brings you to 2 years. I must say that now that we have seen this, we are, of course, a bit more careful. So now we have implemented an actual alert system, so that if we ever see something like this again, we don't dispose it as something I don't know, probably that we are diving into it, a bit earlier. Yeah.
I wonder the light which emits in the ocean, is it also dimmed by the ocean?
It's a very good question. So it's not so much dimmed, but what does happen, like light traveling through air or water, at a certain point, yes, it's dimmed. It's getting absorbed. There's actually 2 effects of light in water. First is what we call scattering, and the other one is absorption. So scattering just means if a photon hits a water molecule, it gets deflected like a tiny little bit. That's what we call scattering. That's also what the word scattering means, right? But then there's also absorption. Sometimes the photon is really absorbed, and then there's less light. There's a nice balance. It's a nice question because there's a kind of a difference between ice and water. Ice is actually, so the ice of the South Pole is extremely transparent. So it really light can really travel for much further than in liquid water. But the scattering length is shorter, so it scatters more. And that's why that's another reason why we built KM3net, is because of this scattering, the reconstructed Cherenkov cone is also scattered a little bit. So the pointing accuracy, so the accuracy with which we can point in the universe where a neutrino is coming from, is a little less in IceCube because of this scattering effect. The good thing is that they can measure more light because it's so transparent, and so their energy estimation is a little better. But and for KM3 it is the other way around. We can point with excellent accuracy, a bit more. The light gets dimmed a bit easier than in ice.
When the neutrino travels through the water, where does the light come from? Is it emitted by the neutrino?
So not by the neutrino, no. So neutrinos, as I said, they travel right through everything. So the neutrinos do not emit light. It's when a neutrino undergoes an interaction with a proton or neutrons or something in the nucleus of an atom, that a secondary particle is created. And as the secondary particle propagates through the water, that starts emitting light. So it's really indirect, right? So the neutrino creates a secondary particle, that creates the light. So it's a double indirect measurement. Yeah.
You mentioned that neutrinos don't really interact with other particles often, mainly rarely. What is the difference between when they don't and when they do? Like, what causes that every millions or millions of neutrinos, they do actually interact?
Yeah. Yeah, okay, I'm not going to go back all the slides, but that's what the silly answer and the short answer is that's what the mathematics tells you. So if you look at that mathematical equation and you start calculating how often such a thing would have an interaction, you get to a very small number. Here's the thing. There's 4 fundamental forces of nature. One is electromagnetism, the other is gravity, and then we have the strong and the weak interaction. A neutrino only undergoes weak interaction. And it feels a little bit of gravity because there's a little tiny mass, but you can really ignore that. The mass is so small, you can ignore it. It's called weak interaction for a reason. It's weak, so it almost never happens. And so when you just put in the numbers of the weak interaction, you just find that the chance that this neutrino interacts with a proton, it's incredibly small. Does that help? It's just a lottery. It's really just a lottery. I mean, the chance is very small, but if you have enough neutrinos, you will definitely find one at a certain time. But the chance is just small. for one neutrino.
Yeah, hello. You showed the graph of the flux and the neutrino energy. You mentioned that the low energy neutrinos are impossible to see, but they have a huge flux.
Yeah.
So wouldn't you be able to think of a small or an experiment that has some random interactions caused by
As I
neutrinos?
said, never tell an experimental physicist that it cannot be done, because people are thinking about it. People are thinking of ways to also measure these very low energy neutrinos. The problem is there's overwhelming backgrounds. That's your real problem. There's a lot of processes at these low energies that come into play. So if you build any detector, you will just find other processes in that material. You always need some kind of material to detect a particle, right? And that will create enormous backgrounds that will overwhelm everything that you have there. But people are thinking of the impossible here. Yes. So more to come, I hope.
Hi, thank you for your talk. So a little bit in the beginning, you mentioned how the distribution between muon, tau, and electron neutrinos kind of scrambles over time.
Yes?
And I was wondering if you know something about the identity of the source neutrinos, can you then kind of extrapolate that? So basically, does the degree of scrambling tell you something about the distance that this neutrino has traveled?
Yes, excellent question. So I put it here as a side remark, this oscillation stuff, but it's a very rich field that I'm actually, this is more like my own field of study, is much more into these neutrino oscillations. And the wonderful thing about these neutrino oscillations is that they are a function, you could say, so the probability that it changes identity is a function of both the travel distance, so the distance that the neutrino traveled, and the energy of the neutrino. So you're absolutely right. If you could measure the mixture at a certain point, and you know exactly what the energy of the original neutrino was, you can actually tell how far it traveled. Or conversely, what we're trying to... So yes, this is things that we're trying to do. And the cool thing about this is that this works both... okay, so now I'm going to explain... Thanks for the question again. I'm going to explain the difference between this smallish detector, KM3net Orca, of the French coast, and the large detector. So the large detector, as I explained, is studying astrophysical neutrinos from the far reaches of the universe. This smaller detector is using these atmospheric neutrinos. The atmospheric neutrinos that were created when the cosmic rays were impinging on the Earth's atmosphere. There was like a free source of neutrinos coming from the atmosphere. Much lower in energy compared to these astrophysical neutrinos. But the really cool thing about them is that you can either look at neutrinos that are coming from right above the detector, right from top. That is a small distance to the atmosphere, only like 15 kilometers. But if I would look down with my detector straight through the Earth, I would see also atmospheric neutrinos, but they would have to travel all the way through the Earth. So you see there that the difference in travel length is 15 kilometers to something like 7,000 kilometers. And that's exactly where we try to see, and we know the type of neutrinos that are created in the Earth's atmosphere. And so we can look at the mixture coming from above and the mixture coming from below to infer something about these neutrino oscillations. And why is that important? Because that will tell us something really important about the fundamental properties of these neutrinos. And this is where really the difference between, kind of astrophysics that people are doing with this large detector and particle physics, where we really want to understand what the fundamental properties of these particles are. So this is kind of where I'm working on. But the cool thing, and that comes back to your question, is that you could also do the same trick with these astrophysical neutrinos, because they also oscillate. They're just neutrinos and they oscillate. And so you can try to infer from the type of neutrinos, I also didn't tell you that, we can actually do some determination of what type of neutrino interacted in KM3net. And so therefore we can also infer about the oscillations. And that tells you something about what happens in the source. Yeah, absolutely.
I was wondering, why do we want to measure these very high energetic neutrinos if we can't trace their source? Or
if you cannot trace the source?
Yeah.
That's actually what we're trying to do. So, can you ask your question? Maybe I misunderstood your question. Can you say again?
I thought you said, like, with the high energy particle, we could not trace the source.
Not yet, for this particular event. No, that's a very good question. So indeed, for this particular event, we cannot really pinpoint the source yet. Actually, I will show you. Here. So in this little plot, you kind of see, so what you have here is coordinates in the night sky. So you just think of it as a square on the night sky. Our event is right here in the center. This is it. But as I said, it's a smallish detector still, and also we have not fully calibrated it yet. So we don't know, so we have a good relative calibration, we call it, but we don't know the absolute pointing of our detector yet. We can improve on that still. So we know that we can improve this, but with the circles that you see here, so the concentric circles centered around this event, are kind of our uncertainties on where this event happened. So we think it happened here, in the middle. That's our, what we call the best fit. But it could also be here. We're just not so sure yet. So that's why we have these circles. And then we try to find, do we have known sources in there? Do we know of astrophysical objects that were discovered by traditional telescopes that were looking at light, right? They also can see these active galactic nuclei, black holes, other galaxies. And so we know of various different astrophysical sources, highly energetic astrophysical sources, and we plotted them here. And as you can see, yeah, there's many in that region. So that's why I say that we don't know how to pinpoint it yet. We don't know exactly what source to associate this event with. But that is the ultimate goal. So what we hope to do in the next years is to better calibrate our detector and to be able to shrink these circles and to hopefully then center on one of these sources and say, that's it, that's the one.
Would you be able, when you do that, to make this event also more accurate? Or is it only possible?
So we can do that retroactively. So we have this data set, and it's really because we don't really know so well where our detecting is pointing yet. But if we can improve that, we can rerun the analysis and make this circle smaller. So we don't need a new event for that. It's an excellent question. So we're actually working on that right now to better pinpoint the detector. Yeah.
Let's have one more question.
Thank you. Earlier you were mentioning that we are actually not measuring the direction of the neutrinos, but the direction of the secondary particles that were there. How do we know that it is exactly the same direction of the neutrino?
That is also a very good question. So how do you know that the direction of the muon is exactly the same direction as the neutrino? That's also a particle physics question. And the answer is, we know it well enough. But we actually take it into account here. So it's something that we definitely take into account. The accuracy with which we can pinpoint is not 100% because indeed there is some kind of energy transfer. So there's a little mismatch, but it's very small. The answer is it's very small.
Does the same go for the energy? Muon versus neutrino.
That's an excellent question. That's a really wonderful question. There's actually a problem because a muon can actually travel quite a long distance. So, okay, yeah, I'm going to show it. I'm happy that I put it in. This is a similar plot that we showed before. So flux on the vertical axis, energy on the horizontal axis. And this is the error bar on our event. It's enormous. So I say that it's 40 times higher, but we could also be a little bit off. So as I said, it's conservative. So I actually we put this left boundary as the 40 times, right? So it's probably more than 40 times. That's why I said it's conservative. The problem with muon neutrinos is that the muon, so as I said, the neutrino interacts somewhere outside of the detector, and then the muon starts to travel. And this is the point where the detector starts, and this is where we start gathering light. The amount of light that you see in your detector is a direct measurement of the neutrino energy. Of the muon energy, sorry, of the muon energy. The thing is, the muon has lost energy already before it reached the detector, right? So some of the energy is gone. You don't know exactly where the interaction happened. So the energy estimation is not so great for muons. However, if you were to detect another type of neutrino, say an electron neutrino or a tau neutrino, your signature is very different. It's not a muon traveling through your detector. It's actually a spherical blob of light in your detector. And that is nicely contained within your detector. And then you have a perfect energy estimation. So the cool thing about these muons is that they point back very nicely, but your energy estimate is not so great. While for other neutrinos, your energy estimate is really great, but you don't really know where it comes from because it's a spherical event. So yeah, it's kind of an art.
Okay, so now on a closing note, thank you everyone for attending. I hope you enjoyed this insightful lecture on neutrinos. If you did, make sure to check out Studium Generale's next lecture, which is going to be on the 5th of March, which is next Wednesday. It's called How We Sold Our Future, and it's titled after the book by Jans Beckert on How We Sold Our Future, the Failure to Fight Climate Change. It's also a very interesting topic, and there's also going to be a panel discussion about this topic. But for now, thank you for attending. I hope you enjoyed it as much as I did. It was very entertaining. And thank you, Daan van Eijk, for your wonderful lecture. And also, if you have more questions, feel free to come to him and ask him. And I know you also have some VR experience prepared. You can also try this out. Yeah.
Yeah, so feel free. So everyone, thanks. Yeah. Did you want to say more or not?
No, just a round of applause for you.
Thank you, thank you. Thanks again. So if you want to leave, you're free to leave. But if you want to ask more questions, I'm here. And I also brought these two VR goggles. And I will help you putting this on. And if you put this on, you will find yourself at the bottom of the sea, very close to the detector. You will see the detector, you can look around, and you can actually see a loop of this event going through our detector, right? And so with these things, with these controls, you can walk around. So if you want, feel free to have fun with that. I'll try to help, and maybe someone can assist me while I answer questions. Okay, so thanks again.